All right, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1203. Hopefully, you guys are doing okay. Had a good 3-day weekend. We had an extra long holiday and Valentine's Day, which hope you had a good Valentine's Day. I had a great Valentine's Day. I'll tell you about that in a bit. Don't worry, I don't kiss and tell. It's not like that kind of story. But I guess we should start with some bad news um, because I just want you guys to know that migraine's acting up today, so I'll be a little bit off and not as excited about the good news that I wanted to share with you of what actually happened on Valentine's Day. So my brother had his first kid. So you guys can all call me Uncle Jhevon now. Yes, yes, thank you. Yes, I worked very hard to make this happen. Okay, so yeah, which is awesome. So I'm a lot more excited than I seem, but that's because, today's one of those days. But yeah, really good stuff, really great. So should probably look excited for the thumbnail. So very good news. More good news. We're going to be able to do more math today. So that's awesome. I know you guys are excited about that. That's why you're all here. So let's actually jump into it. Before beginning, I just wanted to make some announcements because students from some other classes were asking me when the tests were, as well as I had some students from my calculus classes, I don't remember if it's this class or who or whatever, showing up for a test 2 days ago when showing up for a quiz 2 days ago when we didn't. So I just wanted to remind you that you should pay attention to the quiz dates. I'm not always going to announce them, but I expect you to know when they are. The dates for the quizzes and tests, they are set. They're in the syllabus. So you go to the syllabus. In the topics list, you'll see the location of the test. You'll see the date of the test there. And I believe below that table, you'll see the quiz schedule. So you'll see all the dates for the quiz schedule. So we're having 5 or 6, I think 5, but you can check the syllabus to see if I'm correct. Quizzes over the course of the semester. So it's not literally every week, but the dates are there. So make sure that even if I don't remind you, on the day we have quizzes, you show up for the quiz. So I just wanted to make sure you know that. And as for budgeting your time, quizzes can be anywhere from 30 minutes to an hour long, depending on how much stuff we do and how much stuff I want to test you on. So you should expect on average to spend around 30 minutes on the quizzes. But if we cover things where the topic is more detailed calculations and you need a longer time to do stuff, I might give you up to an hour. So I believe they start at 9 a.m. in the morning. So you should expect around between 9:30 and 10 is when they will end. Yeah, so just make sure you know that. Tests are going to be somewhere between an hour and 15 to an hour and 30 minutes long. And again, you know the dates for those. The final exam, we don't currently know the date for that yet. That's not something that I choose. The Fordham decides the final exam schedule. So as soon as I can update you there, I will. But I can tell you now, the final itself is going to be a couple hours long. 2 hours, 2 hours and 15 minutes-ish, something like that. And it's pretty much going to be like a combination of test 1 and test 2, pretty much. So the tests aren't cumulative. The final is, and the quizzes aren't cumulative either. So the quizzes and tests don't overlap unless it's incidental. The final though is everything. Yeah. So I just wanted to make sure about that because there were some students confused about the timing and when we should be doing what. So yeah, I encourage you to go back to the syllabus, make sure you know the dates, put it on your calendar. Don't miss them because remember, there's no makeup for quizzes and there's no makeup for tests unless you have a very good reason. And I forgot is not a good reason because I put it in writing. I mentioned it a couple times in class. You should know when it's going to happen. Okay. Yeah. That being said, here's what's on the agenda for today, and I'm pretty sure some of this is going to spill into tomorrow. We're going to continue doing some limit examples where the next 4 examples, is for me to introduce a different kind of limit that we want to take, as well as I want to discuss some strategies about taking limits. And that's what we call it when we actually compute a limit. We say we take the limit. And we're going to talk about some strategies that we can do. And then we're going to try to put those strategies into practice with a few more examples. And yeah, that will probably spill into tomorrow. But we'll get through as much as we can today, and we'll continue later on. So that's basically the gist of it. But let's remind ourselves where we were. So let's go back to last class. Last class, we officially started calculus. We started talking about limits. Limits, we are going by an intuitive definition, quote unquote. And basically, a limit is what your y value gets close to, as your x value gets close to something. And I did a few examples to really illustrate what that means. Getting close to does not mean that we actually get at the point. Being at the point is not the point, right? So if you think that's the point went over your head. Okay, enough puns, right? So limits care about getting close to something, not actually getting there. So even if there's a hole or our function is not defined at the point, it does not matter. It's possible for the limit to still exist. A limit does not exist if the left and right do not agree. And these left and rights, you can use limits to talk about them individually. These are called the one-sided limits. And if the one-sided limits don't agree, then the overall limit does not exist. That's what we call it when a limit is undefined, right? We say does not exist. However, even one-sided limits in and of themselves might not exist. So for an overall limit to exist, both one-sided limits must exist and they must give you the same value. However, it's possible for various combinations of limits to not exist. For the overall limit to exist, both of the one-sided limits need to work and as well agree on the value. But you can have a bunch of combinations. You can have all of them not existing. And for example, in this case where there was a gap, remember, limits are about getting close, arbitrarily close as you want. And if you can't get close to a point, the limit won't exist at that point. And those were the examples we did last time. So I left you off with these examples to try. Hopefully you tried some of them, so that'll make today go by quicker. But this is what we're going to pick up with now. Yeah, so that's where we are. So let's actually get into it now. Let me make this a little bit bigger. Someone's coming in. So yeah, let's do this. So let's, not sure why it's doing that, but okay. Let's talk about this guy. Okay, looking at the limit as x approaches 0 of 1 over x. And again, just to get the intuition down, I'm going to sketch the graph of what we look like here. I do expect you guys to know what 1 over x looks like. What does 1 over x look like?
You have an L in the first quadrant and then another L that's kind of like looks inverse of it in the third.
So and it's a very curvy L, right? In fact, it looks like this, and it's asymptotic, right? So it gets closer and closer to the x-axis, but never touches it. And on the left, it gets closer and closer to the y-axis, but never touches it. And then the opposite happens down here. And what we care about is getting close to 0 and describing what the y values are doing. We introduced limits last time. So let's actually look at the one-sided limits. If I were to ask you, what does the limit as x approaches 0 from the right side of this guy looks like? What would you say?
Positive infinity.
Positive infinity, right? It doesn't go to an answer, but positive infinity, this is going to be a valid answer for limits for our class. And usually that will be the case. I mean, there are a few situations in which people might think that an infinite limit might as well does not exist and we don't care. But I would want you to know when infinity is an answer as opposed to DNE, no answer exists, because infinity is going to be important when we study asymptotes later on. Knowing that infinity is an answer that you can get. So it's not a real number, but the graph just keeps going up higher and higher and higher. And if I were to ask you, what is the limit as x approaches 0 from the left of this function?
It's minus infinity.
Negative infinity. Just keeps getting smaller and smaller and smaller. That infinity was very weird. So then if I were to just ask you, overall, what is the limit as x approaches 0 of 1 over x? What would you say?
Does not exist.
Does not exist. Yeah. Yeah, okay, awesome. Let's look at another one that can illustrate a very important difference. Let's look at 1 over x squared this time. So what does that graph look like?
An L and then reversed over the y-axis.
Right, so the right side looks very similar to 1 over x. It's not super, I mean, when we draw it by hand, not to scale, it looks very similar, but it's actually a lot steeper. It rises a lot faster and actually decreases a lot faster. And this time you reflect it, right? Because it's squared, it doesn't have a negative part. So both sides are above the x-axis, or it takes the negative side and it squares all the values, so they jump to the positive side. So that's what that looks like. And so I could ask you, what is the limit as x approaches 0 from the right of this function? And what is the limit as x approaches 0 from the left of this function? From the left, what is it?
Could you effectively say infinity?
If infinity, right. As I get close to, remember how we're doing it, as I get closer and closer to 0 from the left, I'm on the function, and then I'm tracking what's happening to the y values. They keep going up. And so, yeah, infinity. Similarly, if I get closer and closer to 0 from the right, I'm on this side of the function. And again, my y values keep going up. Infinity. So if I were to ask you, what is the limit as x approaches 0 of 1 over x squared? What would you say?
Infinity.
Infinity. Okay, so at this point, I just want to again reiterate something. So this is one of the reasons why, note, as x gets close to 0, 1 over x squared gets close to 1 over 0. It never actually gets there because we can't divide by 0. But the fact that this gives us infinity as an answer is why a lot of people think, oh, I can divide by 0 and get infinity as the answer. But this is not correct, right? I want to again emphasize, we do not actually divide by 0. We just get close to it. In fact, how you would write it, in fact, 1 over 0 is incorrect. Preferred. You can write 1 over 0 plus, and then tell me that that's infinity. because that doesn't mean divide by 0. It means you divide by 0 with a little bit of positive thing attached to it, right? And because the denominator is squared, that's what we have, right? So that 1 divided by a very small positive number gets bigger and bigger the smaller the number gets, right? You can't actually plug in 0. Similarly here, you can note that as x gets close to 0, 1 over x approaches 1 over 0. Again, we don't actually divide by 0. So on the left, what we have is 1 over 0 negative. So it's a very, very small negative number, and it's getting smaller. So that's what that notation actually means. And that is interpreted as negative infinity. 1 over 0 positive on the right. That is interpreted as positive infinity. But 1 over 0 by itself is meaningless and incorrect. So never actually divide by 0, ever, right? And another thing I want you to appreciate here is that they both seem like they approach 1 over 0, but they have two very different behaviors. In one case, it looks like we can have some sort of meaningful answer. It's not a number, but it tells us about a behavior, infinity. It's suggestive, as opposed to this one that DNE doesn't even have an answer. It doesn't even make sense to talk about this, right? I can talk about it one side at a time, but I can't talk about it in general. So that also goes to show you that even when we're getting close to dividing by 0, crazy things can happen, right? You don't always get the same situation. You don't always get infinity as a result. So again, this idea of division by 0 is equivalent to infinity is very flawed, right? So that's one thing I wanted to also point out to you about this example, or these two examples taken together, right? So unfortunately, these are the kind of examples that causes people to think that division by 0 is a thing that can work, but it cannot. And even if you get close to trying to get it to work, the situations can vary a lot. And we'll actually see more examples in the future of this happening. That being said, let's move on to another example. How about this one, which seems like very strange at first. But I think because of how limits work, we kind of know what this really means, right? Limit as x approaches infinity. This isn't even a number, right? It's not like x approaches 0 or x approaches 5 or x approaches 2. X approaches infinity. What does that mean? Well, again, we can graph this. Keeps going. Now, x approaches infinity means we're going far to the right. X going off to infinity. We just keep going, right? So we're not approaching a number. We're going far to the right. Are we there yet? No, we're not there yet. Are we there yet now? No, we're never going to be there. We've traveled a gajillion, bajillion, kajillion, kachillion. Are we there yet? No, keep going, right? That's what x approaches infinity means. Keeps getting bigger and bigger. Can you tell me what the y value is doing? What is the y value getting close to?
0.
0, right? Notice that if we're on this function and we keep going off to the right, and then we backtrack that to the y-axis, what is happening to the corresponding y values? Notice that they keep going down, but they don't just go down forever. They kind of accumulate somewhere. They're never here. There's never going to be a point where it hops to the negative side because the right side of the graph never goes to the negative side. So the y value is definitely bunching up somewhere. And as you can see from here, it goes to 0. it's very important that you realize the function itself will never actually be 0. A fraction can never be 0 if the numerator is not 0. The numerator here is 1. But again, the limit doesn't care about getting there. The limit cares about what are we getting close to. As we square a number and that number gets bigger and bigger, and we put that in the denominator of a fraction, the fraction keeps getting smaller and smaller and smaller, but it stays positive. So it approaches 0. Right? Not that it ever gets to 0, but that's what the y values are getting close to.
And that would just be basically because the y values are going like 0.1, 0.01, 0.001, basically.
Yeah, and smaller than that and just keeps going, yeah. So as the x keeps going to bigger and bigger numbers, like gajillion, bajillion, gajillion, the y starts going to a gajillion zeros and a 1, right? And then it keeps getting bigger. So as x gets bigger, I mean, maybe I should say larger. It's not an English class. As x gets larger, 1 over x squared gets smaller, but stays positive, which means it gets close to 0. But 0 from the right side. It's always 0 with a little positive charge. But you can never stop at a number above 0 and say that's the answer, because eventually you'll get closer to 0 by making your x a little bigger, right? So the limit has to be 0, right? That's what the y values are getting closer and closer to. Okay. Let's do another example. And then I'll introduce the concept that this set of examples are about. Or let me just do this one. Or you guys do this one. Tell me the answer. Limit as x approaches infinity of e to the x. Maybe I'll throw in another one as well. Limit as x approaches negative infinity of e to the x. Do those quickly. Tell me what you get. Include a graph in your answer. Graphing is going to be important later, so let's not lose the ability to graph stuff. So limit as x approaches infinity of the function e to the x, and then do same function, but limit approaches negative infinity. Tell me what you think the answer is, and draw a picture. Okay, do we have answers yet?
Is the first one infinity?
First one is infinity. What does the graph of e to the x look like?
L that intercepts through E and then goes up.
No, not quite. And it's not really an L. Well, I guess it's kind of like a backwards L, if that's what you want to say.
Yeah, basically.
And so how does it go? Like this?
No, like on the x-axis, but never actually hitting it.
So it's right above the x-axis and goes up like that, right? Okay, now you said it passes through E. When it hits here, what is the value?
One.
It's 1. How do you know? I just memorized it. Which might work for this class, but you should kind of know that will be important later. Why? Why is it 1? Why is it not E or something else? In fact, E, remember, that's roughly 2.718. So E would be a little bit higher. And you can probably tell me when that value happens, what coordinate actually has E as the output. It's also useful for your homework to think about it. So it's probably going to be more relevant quicker than sooner rather than later. Why is it 1 on the y-axis? And tell me when does it hit E? Shouldn't take you too long if you understand the concept of what a graph is. So not expecting anything too complicated here.
It's E when X is 1.
Yeah, so that's 1. Now why? Why does it hit 1 on the y-axis? And why does it hit E when the x value goes to 1?
Because it's 1 because X is 0 in that case, because
Right, and E to the
0
0 is 1, right? We looked at that. That was a law of exponents. X to the 0 equals 1 whenever your x is not 0, right? So that's a rule that we have. So it's that because we know that because of we plug in the answer and we know based on the laws of exponents what that answer should be. So when my x is 0, I plug it in. I get e to the 0. The result is 1. To get e, I need e to the 1. That was another law of exponents. X to the 1 is x. So if I want to get e, the base, then I would just plug in 1, and so the answer would be e. So yeah, so remember how graphs work. You plug in the x value to figure out what the corresponding y value is. Okay, so that is that. Now, as you can see, as x is approaching infinity, so x just keeps getting larger and larger and larger, so x keeps going this way, it means on our graph we keep going this way, which means on the y-axis we keep going that way, which infinity is the answer, right? The y values keep getting bigger and bigger. What about the second one? So now we see this picture right here. You know, it passes through here at 1. Limit as x approaches negative infinity. What's the answer? So limit as x approaches infinity is infinity, right? So the limit as x approaches negative infinity is
0.
0. I was wondering if anyone was going to say negative infinity, kind of like a linguistic trip up there. 0. Why 0? Because as x goes to negative infinity on this side, that means your x values are getting bigger and smaller and smaller and smaller, technically, more and more negative. It means on the graph you're doing this, which means on the y-axis you're doing this, and you are approaching that spot. So 0 is the answer. Okay, so hopefully now we're getting an idea of what a limit is, how it works, how to intuitively tell it if we know the graph, which is going to be a strategy that might come in handy more than you realize. But yeah, that's basically it. And these limits here introduce two new concepts that I want you guys to be aware of. Obviously, infinity is coming into the mix, and these guys have a special name. The above examples introduce two concepts. And this is the idea of infinite limits and limits at infinity. Okay, so let's actually talk about that. The limit as x approaches a of f of x equals L is an infinite limit if your L is plus or minus infinity. So when the output, the y value, the limit value blows up to infinity, we say it's an infinite limit, right? What's the limit? It's infinite, right? Goes big. Then if we look at the limit as x approaches a of f of x equals L is a limit at infinity if the a value is plus or minus infinity, right? So that says we're taking the limit at infinity. It's not at x equals 0 or x equals 5 or x equals blah, right? It's not there. It's at infinity, right? So if your limit goes to, if the input goes to plus or minus infinity, it's called a limit at infinity. I'm taking the limit at infinity, right? And what's going to happen, it will do whatever we calculate it to do. You should note, maybe I should actually also, I'm writing lean again. Oh my God. Yeah, that's very lean. So example of an infinite limit is the limit as x approaches, limit as x approaches infinity of e to the x, limit as x approaches 0 of 1 over x squared, right? Those are all infinite limits. Limit as x approaches 0 from the negative side of 1 over x. These are infinite limits because the answer is infinity, right? For examples of limits at infinity, well, limit as x approaches infinity of e to the x is such an example. In this case, it gave you infinity as the answer. Limit as x approaches negative infinity of e to the x is another example. This was 0. And limit as x approaches infinity of 1 over x squared, that's 0. So these are all limits at infinity because the x is approaching infinity. And I do want you to note here, it is possible for a limit to be both, right? And I already gave you an example of such a thing. Example, the limit as x approaches infinity of e to the x equals infinity is an infinite limit at infinity, right? So at infinity, it goes off to infinity, right? So when my x goes to infinity, my y goes to infinity, right? This is a limit. This is an infinite limit at infinity. Okay, so those are some concepts. It's important for you to distinguish these two in your mind because there are rules that only apply to finite limits. Okay, so knowing when infinity is in the mix, you do have to deal with things differently. So we call them by different names, so you will know. Okay, And let's move on. Let's talk about some properties. And I don't know how far I would get. I'll at least discuss some strategies and we can start the examples. Let's look at some properties of limits. Getting ridiculous now. Let's try again. Yeah, that looks straighter. Let the limit as x approaches a of f of x equals L, and the limit as x approaches a of g of x equals M, be exist and be finite. So this means they're not infinite limits. Okay, so suppose we know the limit of f as x approaches a and the limit of g as x approaches a. They're both give us numbers, right? And let c be a constant. Then the following hold. So let's look at some properties of limits. And by properties, I mean algebraic properties. How can we use them in calculations? What can I do with them? What can I not do with them, etc. It turns out limits are actually really, really nice when we talk about their algebraic properties. Almost anything goes. What do I mean by that? You're going to see. So here's the first thing. The limit as x approaches a, oh God. The limit as x approaches a of a constant is the constant, right? If my y value is always c, what is my y value going to approach when my x value approaches literally anything? Well, c, it's always c, right? So that makes intuitive sense, but you should just know the limit of a constant is always just the constant itself. What is the limit as x approaches 17 of 5? Well, it's 5. It's always going to be 5, okay? So that's the first thing. 2, here's something you should know. The limit as x approaches a of c times f of x, right? So if I have a constant times a function, it turns out we can factor that constant outside. Right? So I'd be able to say the answer here is c times L, which is going to be some other number. Constants can factor in and out of limits. Just like you can factor constants in and out of parentheses, you can factor them in and out of limits, which is super cool. So here's another thing. Limits actually distribute across sums, which is awesome, because we like doing that even when we shouldn't. So if I have a limit of a sum, it's actually equal to the sum of the limits. The limit notation, you can actually distribute it. So you can take, if you have a sum, you can take the limit of each part, right? So that would, if you know the answers to the previous limits, this is just going to be L, and then you add the other guy. 4. As if it wasn't already amazing enough that it distributes across sums, here's something that's cool. It also distributes across products. Which, I mean, should already be amazing to you, I think. Not a lot of things do both, right? So this would be L times N. Not a lot of things do both of these, distribute across sums and products. Remember, powers don't distribute across sums, but they do across products. Radicals doesn't distribute across sums, but they do across products, right? a constant multiplier distributes across sums. It does not across products, right? So there are a lot of things that we know that does one of these things, but it turns out limits do both of these things. So they're very nice. Almost anything you would kind of think about trying with a limit is actually going to work out mathematically, which is good, as long as they are finite. These rules do not apply when the limit is infinite. Of course, since it distributes across multiplication, I do want to state that it does distribute across division. So if you have a limit of the division, you can take the division of the limits. Right, which would give you L over M, as long as M not equals 0, of course. Right? So I know M is a finite number, but of course, if I'm dividing by M, it can't be 0. So generally, you don't assume that you know what the value of a limit of a division is if the bottom is going to 0. We're going to deal with those situations, by the way. We already did some examples of that. 6. It turns out that limits can also pass through powers, as in like radicals or other powers and things of that sort. And to make sure that don't have to worry about complex numbers, we're always going to assume the power is positive. But if I have some function and it's raised to a power, it turns out I can move the limit inside. Just do the limit of the inside and then raise that answer to the power, which is going to be L raised to the n, if n is greater than or equal to 0. Or let's just say greater than 0, right? So these are the properties of limits, and limits are one of the nicest things that you'll ever come across in mathematics, because almost anything goes. Distribute out whatever you want, factor out whatever you want. Doesn't matter. If it's a constant, don't do anything. Yeah, limits are really nice in this way, right? They have very nice properties, and you can do a lot with them. Factor constants out, they distribute across sums, they distribute across products, they distribute across divisions as long as you're not dividing by 0. You can move them in and out of powers, in and out of radicals. Like almost anything goes, right? Which is very nice. Not a lot of things are this nice, but limits are that nice. So that might be useful for more complicated limits that we'll be doing in the future. So if I ask you to take the limit of a bunch of stuff being added together, you should know you're able to take the limit of each individual part. And as long as all of those give you a finite number, you add all those numbers together, that's your answer. Okay, so that's nice. So these properties tell you how you can actually do computations with limits. Okay, now let's talk about strategies of limits, because as you're going to realize, you can know about how limits work and you can know all their properties, yet I can give you a problem to ask you to find a limit and I don't know how to begin, right? It's very complicated to know which property to apply when, right? So to figure it out can get challenging. So far, we've been doing very simple examples because I really want to introduce the concept to you, but the examples are going to look more complicated. So I will be expecting you to take limits of things that look like these, right? Which is really crazy, right? So the properties are going to come in useful in that situation. But again, just knowing which property to apply when is in and of itself a part of the problem solving challenge, right? I don't know what I should apply when. What do I do? How do I find this random particular limit, right? So that's what I'm going to talk about now. And then I don't know if we can get through an example or two, but we'll pick up with whatever we don't do tomorrow. I see you guys tomorrow. So let's look at strategies. Let limit as x approaches a of f of x be some random limit we want to compute. Right? So it can look like anything, right? So random problem shows up on a test or a quiz or a homework. How do you attack it, right? Well, there is like a best practices kind of thing. There are certain ways you want to approach the problem, certain things you want to think about first versus second versus third that can make your life a lot easier. And if you practice these steps, you'll become an expert at solving limits relatively quickly. So here is the first thing. And I'm first going to use a phrase that we have to define fully later, but I'm going to mention it in intuitive terms at this point. If f of x is continuous at a, then the limit as x approaches a of f of x equals f of a. So essentially, step one, try to plug in a. That's basically what it boils down to. If you can, that's the answer. Usually. Right? Our very first example is like this. Remember when I asked you to find the limit as x approaches 2 of the function 3x plus 1 or something like that? And we realized the answer was 7. And we're like, hey, we could have just plugged in x equals 2 and get that. The reason is because the function 3x plus 1 was a continuous function. We'll define in detail later. Basically, this means I can plug in the x into the function and get a meaningful answer. And at the same time, the function connects on both sides. So there's no gap, there's no break, there's no jump. There's something, I'm in a situation where I can get close to that point. And when I get there, the point is actually filled in, right? So which a lot of the functions that we're looking at have that property, right? So pretty much anytime you can plug in the number, that will be the answer. However, if you have a piecewise function or something a little bit more complicated, it might not be the answer because there might be a gap or a jump or something. But most times you just try to plug in. If it works, that's going to be the answer. We'll talk about continuity in more detail later and you'll get a better idea. However, what if, I don't think we're going to get to any examples. After I tell you about the strategies, we will, I'll let you guys go. Example, we looked at limit as x approaches 2 of 3x plus 1. Well, that's just 3 times 2 plus 1 equals 7. You're allowed to do that because 3x plus 1 is continuous. Step 2. If you can't plug in, try to simplify so you can plug in. Simplifying doesn't fix bad points, but the limit doesn't care about being at bad points, so we're cool. Example, we looked at one. Limit as x approaches 2 of x squared minus 4 over x minus 2. This is the same as a limit as if I did this and started to simplify stuff. Cancel. This is going to be the same as this. And then now I'm in a situation where I can literally plug in 2. Y equals x plus 2 is a continuous function, so I can just plug in 2. And 4 was the answer, right? So we did a very long-winded way of getting to that answer before, but now you should know this is the shortcut. You could actually just do this. Just simplify, and if you can get something that you can plug in, awesome, do it. That's going to be the way to go. Step 3. Maybe I'll just call this a fact that we're going to talk about later. Step 3. So either you can plug in directly, and great, that's an easy problem. Just compute the answer. Or maybe you can't plug in because you'll divide by 0. What you try to do is simplify so that you can plug in. And sometimes that's going to be your answer. Not always. Sometimes you'll need a special technique. I'm not going to tell you about those now, but we'll discuss some later. actually want to do some examples to motivate the special technique. And we'll actually do one later in the semester after we learn some more calculus. But there are some special techniques we can do now. Step 4 or 5, depending on what's easier at the time, you can use a graph or table of values if graphing is hard, right? So obviously, if I ask you, what is the limit as x approaches 0 of 1 over x squared? The graph of that is easy. You'll know it in your head and you'll be able to tell the answer right away. However, if I gave you something way more complicated, a graph isn't going to be as useful. However, you can actually do a table of values and get close to it. Let me show you a quick example of how that would work with something that we already know. Let's say x is approaching 0 of 1 over x squared. We know that the answer is infinity, but how would we figure that out? What we could do is a table of values. Here are my x values, here are my y values. Here is where 0 happens, and I don't know what the y value is doing. What I can do is I can plug in a bunch of numbers close to 0 and then compute the y value. So let's say I led myself up to 0 by doing something like 0.1, 0.01, 0.001, right? So that's like 1 over 10. This is like 1 over 100. This is like 1 over 1,000, right? If I plug that into my y function, this would become, well, 100. This would become 10,000. This would become 1,000,000. Notice that these guys are just getting bigger and bigger. As we approach 0. So basically, we're heading off to infinity from this side. But of course, you know about one-sided limits. It's not good enough to just check one side. So you do the same thing from the other way. So you go in and you plug in like minus 0.001, minus 0.01, minus 0.1. However, because you're squaring, you actually get exactly all the same values, right? So this one is going to give you 100. That's going to give you 10,000. This is going to give you 1,000,000. And again, you realize that moving up, we're heading to infinity. So because these guys are the same, from that, you can conclude the limit is infinity, right? But it might approach some other number. It might be getting close to 2. You might see it going 1.9, 1.999, 1.9999, 1.9999. From the other side is 1.9, 1.999, 1.999. And you're like, these guys are getting closer to 2. So you can actually just do a table of values. And from that, you can figure out that the answer is going to be infinity. I will say graphing is easier for this particular example. We actually did that. Right? You graph it, you see that both sides are going up. You can tell it's infinity right away. But let's say you don't know how to graph the thing that you're looking at. You can actually just plug in numbers into the function, getting closer and closer to what the x value is, and then see how the y value reacts. Remember, that's what a limit is. It's the y value we approach as the x value is doing something. So just track the y values, right? And you can do that by a graph or a table of values. And the last thing, step 6, and I think this would count as a special technique. Know, I was going to spell that one in. And this is the last tip. Know about the behavior of functions and exploit. Useful is something I mentioned before. Remember logs, they grow slower than polynomials, which grow slower than exponentials. And in fact, these grow slower than something called factorials. These go slower than something called like an exponential with a changing base, right? And this is as x goes off to infinity, a greater than 1, okay? So the guys on the right are bigger than the guys on the left, so big that the guys on the left are like 0, effectively 0 compared to guys on the right when x gets bigger. We looked at this concept before. So how can you use that? So here's an example of how you can use that. What if I say the limit as x approaches infinity of x to the 7th over e to the x plus 1? Well, this guy, one thing I want you to notice is that the top approaches infinity and the bottom approaches infinity. But infinity over infinity is not something that we can actually determine right away. We'll talk about that a little bit more later. However, I know the top is a polynomial. The bottom is an exponential. And remember, exponentials win. This guy wins. What does winning mean? They're both approaching infinity, but the e to the x approaches infinity so much faster that the x to the 7th is effectively 0. X to the 7th is effectively 0. Compared to the e to the x plus 1. And so essentially what this means is that the limit as x approaches infinity of x to the 7th over e to the x plus 1, I know the answer is 0 with very little calculation because I understand there's an exponential in the denominator. The denominator is going off to infinity. The numerator is essentially 0. So I have 0 divided by infinity, 0, right? And I can just say here, bottom heavy. And in this class, to me, that's enough showing your work. If I put this limit on a test and you say the answer is 0 because it's bottom heavy, because it is, the bottom is a lot heavier than the top, you know that 0 would be the answer. In the reverse case, it will be top heavy, right? So similarly, if I had asked you the limit as x approaches infinity of e to the x plus 1 all over x to the 7, you would tell me that it's infinity, and you would write top heavy beside it, and that's, for our purposes, showing your work, right? Because you're at least telling me you understand what concept is being applied. You didn't just randomly guess 0 or infinity, right? But just me knowing about how functions relate to each other, knowing the difference between an exponential and a polynomial, allows me to answer this question like that, right? Didn't have to graph, didn't have to plug in a table of values, didn't have to do anything complicated, right? I couldn't actually plug in infinity because it's not a number, but just knowing about the functions, I know how to answer that question, right? So those are the 6 main steps. Yes.
I have to leave for a class. That's okay.
Yeah, that's okay. I'm actually done now.
Oh, okay.
What I would like you guys to do though is what I'd like you guys to do for tomorrow, sorry, I was getting a call. Try these guys based on the strategies that I mentioned to you, and we'll go over them together tomorrow. I'll leave it in the notes, of course. And that's it. We are going to wrap up there. Thank you for your attention. Yeah, have a good rest of your week, good rest of your day, and I'll see you guys in the next one. Ciao.